I want to say thank you to the organizers for making this school possible. I'm very glad to be here with all of you guys. It's a great pleasure for me. So I will talk about this special kind of left orderable that was introduced by Andres yesterday. So let's recall the definition. We say that a left orderable group has the Conrad property, or its C-order, or its Conradian, if for all pair of element positive in the group, there exists a natural number such that its inequality holds, right? So this is a little weird definition, but well, one of the exercises from yesterday, it's proof this, that it's, we can change in the definition the number n for only 2, right? So I will give a proof with an idea of Jimenez that it's a student of Anders, and it's a very beautiful idea. So let's suppose that there is 2 positive elements that don't have this inequality. So this must happen, right? So we can change that inequality for this because the left invariance, and because this is a positive element, this not a positive element because the positive element are semi-group, but this it's less or equal to the identity, right? So this element must be negative, so we can find this inequality, right? Okay, so with that in mind, we can construct some element positive. This element is positive because it's the product of 2 positive elements. And we can show that the pair G and this H don't satisfy in the Conrad property. So if we take the exponent 1 of this, we have for the left invariance and this inequality, that this must happen, and this is rewriting like this, right? And for 2, we have this expression, and sorry. Also, I can use this inequality in this step, right? For change this for only an f, and after that we have this, and remember the original inequality. So this element is less or equal only for less or equal to f. So this must happen, and this is the power of 2 of each element. And for all n greater than 2, we can repeat this argument. We split the power in this way. We can use again this inequality for this, and after that we use again the first inequality, right, for making this less or equal to this if, and we can iterate this process until we get this, that it's h. So no one power of h hold the inequality that must happen in a Conrad order, right? So if we have some element that doesn't satisfy in this inequality, it's not a Conrad group order, sorry. So with that, every Conrad group and every Conrad order must satisfy this inequality, right? And well, this proof is again for a student of Andres. And with this, we can prove something about the topology of the Conrad orders in the space of left orders. that the family of 3 orders in a left ordinable group, it's a closed set of the space of orders. So only we need to see that this set of the orders such that an element if f and g are positive, and this inequality also hold, it's equal to this intersection of subbasics of the topology, because this is an open set, and for the previous proposition, we proved that the complement of the C order are the union of all of these sets, and this is a union of open sets. The Conrad order must be a closed set in the space of all orders, right? Okay. Question so far? Okay, thanks. So, well, the next one is establish another characterization of C orders. So for that, I will define this weird subgroup. So if we have a subset of a group, we define C generated by S as the smallest semigroup that satisfies these two properties. S is a subset of this semigroup, and for all elements on the semigroup, the element f minus 1 times g times f squared also belongs to the semigroup, right? It's like a weird semigroup generated for S, okay? So the characterization that I want to prove is this. Gamma admits an C order if and only if for all finite subsets of elements different from the identity, there exists a collection of exponents such that the identity element don't belongs to this semigroup, this weird semigroup generated for this element to the exponent, right? So this direction is the easy one. If we take an C order and a finite subset, let's take this exponent such that these elements are positive. By the proposition, we can see that the set of the semigroup of positive element satisfying the two properties of this weird set, because all of this belongs to the positive for construction, and for the proposition 1, for all positive elements, we have also that this element is a positive, right? So this weird group, semigroup, must contain in this semigroup that doesn't contain the identity. So this semigroup doesn't contain the identity, right? The hard one is the other direction. So let's say any finite subset and a compatible exponent such that the identity element don't belongs to this semigroup. And we define this set like function signs of the all. Sorry, I must be without the identity, such that the function signs is like the, I can write in this. Jacobi. A function sign of gamma to, it's a function such that sinc of g is different to sinc of G minus 1. And if we have G and F such that the sign of this element are equal, then sign of the product it's equal to this. And this is an equivalent definition of a left ordinable. We can show that this defines a compositive, like Andres constructed in a few moments. So with this, I will construct some order that has the property of be left order, but also a Conradian order. So I take this function signs, and this function there exists because we know that this the identity element don't belongs to this semigroup. Okay? So we can take this set like the union of all of this for all the possible election of the exponent compatibly with this property, right? So we can show, as an exercise, this is a closed set in the set of in this set. Ya perdí el his. Sorry. It's a closed set in this. That is a compact set. And also, if we have a finite family of these sets, we can show that there exists some suitably function sign that belongs to here, and this is a subset of the intersection of all of this. So this family of closed sets has the finite intersection property, because it's in a compact set, there must be an element in the intersection of all of this. So I will take this function sign in the intersection of all of these closed sets, and the remark is that that sign defines an order that it's a Conrad order. So for that, every element in the positive, like this, it's basically the sign of if and h it's plus. We have that this happened because the construction of this semigroup. So for the construction, the sign of this must be a positive. So we have this inequality, so we have this. So this must be a C order. Okay? So if we have this weird condition about the election of suitably exponents for every finite family, in here, such that we can have this. There is a C order defined by this in all the group. Okay, so it's a very weird characterization, but it's very useful for the last theorem I want to talk. So this actually it's another characterization, but the reverse will be proved by Andres maybe tomorrow. I don't know, but it's more complicated. So if we take a locally indicable group, then we can construct and C order in gamma. So for that, we will prove that the weird condition about the suitable exponent for every finite subset can be constructed, right? Locally indicable, I remember it's for every finite subgroup, there exists some non-trivial homomorphisms to R with the structure additive. Finitely generated. Yeah. Sorry. So, well, we take a finite subset of the group, and we have for the locally indicability that there exists an homomorphism from this finitely generated subgroup to the R that is not trivial. Let's take if there is any index such that the homomorphism sends these elements to 0. So also for the locally indicability, we have another map that maps this subgroup finite generate to a non-trivial way to the R, and we can follow this process and so on, and this process must finish because at most cada steps must be done, right? Because the size of this set is k, so at most in k steps we can stop, and for all elements in this finite family there exists an index such that some homomorphisms send the element to an element different to 0 for the construction. So in this moment, we chose the exponent of gi as the exponent such that this homomorphism sends this to a positive element, and we take this, the semigroup we generate for this, and we need to prove that the identity element don't belongs to this, right? So first of all, there is two properties. If we have these two elements and the homomorphism has this in his domain, we have that the homomorphism of the product must be equal to this, and it's positive because this it's positive for all the homomorphisms, and also this element that is equal to this must be positive in this homomorphism, right? This is only because the homomorphism sent to minus phi of f plus h plus 2 phi, and it's equal to this number because it's in the real numbers, right? Okay, so if there is an homomorphism that had this element in his domain, the homomorphism sends to something 0 or positive, right? So let's take any element in this weird semigroup. If phi1 of h is equal to 0, this implies that this h must be in the weird semigroup generated for the g's whose has index that the first homomorphism sends to 0, right? Because in other way, phi1 of h is positive. So, well, for the same argument that above, we have that phi2 h, because lives in here, belongs to the domain of the homomorphism phi2. So this is a greater or equal to 0. If it's positive, we must stop. If it's 0, this implies that h lives in the next semigroup, this weird semigroup. But eventually we find an index such that an homomorphism in this element must be positive. So this element, it's different from the identity because this is a homomorphism, right? So every element in this must be different from the identity, and that is what as we want for applying the previous characterization. And I think that is all of I want to say.